Have you ever noticed how the devices we use every day, our phones, smartwatches,
Yeah.
they just keep getting faster, smaller, more
It
powerful?
really feels like this relentless march forward, doesn't it? Always trying to cram more power into less space.
Exactly. And for this deep dive, we're focusing on something that could be, well, a huge part of that next step. It's a material maybe not everyone's heard of, but it promises to go way beyond what silicon can do.
That's right. We're talking about black phosphorus.
Okay, black phosphorus. Sounds interesting. So you're saying this could be a building block for, like, next-gen electronics?
Absolutely. It has massive potential. Think even more energy efficient devices capable of, well, stuff we're probably just starting to imagine.
So our mission today is to really get into some amazing research on this. It's from a team led by Changsun Chen and Teng Zhang over at the School of Integrated Circuits, Shanghai Jiao Tong University.
Right. And their work was published in Nature Materials just recently, August 2025. They tackled a really big challenge. How do you actually make the tiny, super efficient parts needed for future tech?
And their answer involves nanoribbons, made from this black phosphorus.
Exactly. They came up with this really clever new way to make them.
Okay, I'm intrigued. I think you listeners are in for some real aha moments here. We're talking about how stuff at the atomic scale can genuinely change, our whole technological future.
It's pretty fascinating stuff, how manipulating materials that tiny can lead to these huge leaps in performance.
So let's start at the beginning. Our gadgets already seem pretty amazing. Why do we even need a new solution? What's the problem we're trying to solve here?
Well, fundamentally, every electronic device runs on billions of tiny switches. They're called field effect transistors, or FETs.
Right, the transistors. Billions of them in, like, my phone chip.
Billions. And their main job is just turning electric current on and off, but they have to do it incredibly efficiently. The smaller, faster, and more efficient they are, the better our devices work. We're always pushing to shrink them down.
Okay, makes sense. And this is where black phosphorus, or BP, comes in. We hear so much about silicon. What makes BP special?
Well, BP has really excellent physical and mechanical properties. It makes it a fantastic candidate for these next-gen FETs. It's a semiconductor, like silicon, but it has this interesting layered structure, a bit like graphene, but with its own unique advantages.
So if it's got so much promise, what's been the holdup? There's always a catch, right?
There is, yeah. It's something called the band gap challenge.
Band gap. Okay, explain that.
Think of it like an energy hurdle. Electrons need to jump over this hurdle to flow through the material. For a transistor to work really well to be a good on and off switch, you need a very specific band gap size.
Why specific?
Well, if the gap's too small, the switch leaks current even when it's off, which wastes power. If it's too big, it takes too much energy just to turn it on. For the logic chips in our devices, BP generally needs a band gap bigger than 0.5 electron volts.
Ah, okay. So without that minimum gap, your phone battery would drain super fast, even when you're not using it.
Basically, yeah. You need that clean off state.
Got it. So finding that sweet spot is crucial. You mentioned a 2D dead end earlier. What was that roadblock about?
Right. So in theory, you can get the right band gap from 2D black phosphorus if you make it unbelievably thin, like no more than 5 layers of atoms thin.
5 layers. That's incredibly thin.
It is, and that's the problem. It's super difficult to actually make large sheets of BP that are consistently that thin. When you try to make a big area, it tends to get thicker in spots or tear, and then the band gap isn't right anymore.
So it's like trying to roll out a giant, perfect sheet of phyllo dough without any wrinkles or thick bits.
Yeah, that's a good analogy. It's a real fabrication nightmare at that. Exactly like that. Ultra thin strips. And they offer a huge advantage. Their band gaps can be much larger, and crucially, you can tune them over a really wide range from 0.3 up to 3.9 electron volts.
Whoa, hold on. 0.3 to 3.9? That's a massive range compared to the 0.5 minimum you mentioned. How does just making it a ribbon shape give you that much control?
It's pretty wild, right? It boils down to something called quantum confinement and also edge effects.
Quantum confinement. Sounds complicated.
It basically means when you squeeze electrons into such a tiny space, like these narrow ribbons, their energy levels change dramatically. They behave differently than they would in a big sheet. And the edges of the ribbon also have a unique electronic structure that influences things.
So the aha moment here is, just by controlling how wide the ribbon is, you can precisely set the band gap you need.
That's the key insight. You can dial in the perfect band gap for a transistor just by changing the ribbon's width. You don't need to fight with making perfectly uniform large 2D sheets anymore. The shape and the smallness do the work for you.
That is genuinely clever. Okay, so these nanoribbons sound like the answer. What was stopping people from using them before this new research?
Well, the problem shifted. If making perfect 2D sheets was hard, making perfect nanoribbons was also really hard, just in a different way.
Ah, okay. How so?
Previous methods, things like trying to carve them out nanosculpting or using electron beams, tended to produce ribbons that were, well, not ideal. They might be too short or too wide or have rough, jagged edges.
And jagged edges are bad.
Very bad. They can trap electrons, mess up the current flow, make the device inefficient. Plus, those processes often contaminated the ribbons, which is another big problem for sensitive electronics. It was like trying to cut microscopic guitar strings with chunky, dirty scissors. You just couldn't get the precision needed.
Okay, so that sets the stage perfectly. We needed a way to make these nanoribbons narrow, clean, and with smooth edges. And this is where the Shanghai Jiaotong team, Teng Zhang and Changsun Chen, came in with their breakthrough. What do they do differently?
Their approach was really smart. It started right from how they grew the initial bulk black phosphorus crystals.
They didn't just grow standard crystals.
No. The team at the School of Integrated Circuits, Shanghai Jiaotong University, controlled the cooling process very carefully. They introduced a specific temperature gradient during synthesis. What this did was subtly introduce a tiny amount of pre-stress into the crystal structure.
Pre-stress, like they built in a slight tension.
Exactly. Specifically along one atomic direction called the armchair direction. Think of it like slightly stretching the crystal lattice along its length. This tiny built-in tension was the secret sauce.
Okay, so they engineered a sort of tear-here line into the crystal itself. That's brilliant.
It really is, because then they used a technique called sonochemical exfoliation. They hit the bulk crystals with ultrasonic waves, 50 watts of power, for about 6 hours.
So intense sound waves.
Yeah, but it wasn't just shaking them apart randomly. Because of that pre-stress along the armchair direction, the sound waves caused the crystal to literally unzip cleanly along the perpendicular direction, the zigzag direction.
Wow, like using a sonic scalpel to open a zipper that was already designed to split that way?
That's a perfect way to put it. And this method, which they published in Nature Materials, wasn't just clever, it was incredibly effective.
How effective? What was the result?
Get this. The yield was up to 95%.
95%. Seriously?
Seriously, almost all the starting black phosphorus material successfully turned into these high-quality nanoribbons. That's almost unheard of in nanomaterial synthesis. It's like buying a bag of chips where pretty much every single chip is perfect.
That's incredible. That shifts it from a lab curiosity towards something you could actually, manufacture.
Exactly. And the precision was amazing, too. They produced large amounts of these BPNRs. The average width was around 72 nanometers, but they could make them as narrow as 1.5 nanometers.
1.5 nanometers. I can't even picture that. How wide is a human hair again?
About 80,000 nanometers. So yeah, these are incredibly tiny. And crucially, they had nearly atonically smooth edges, especially the ones between about 7 and 340 nanometers wide, with that well-defined zigzag edge structure.
And smooth edges mean better performance, right? No jagged bits to trap electrons.
Precisely. Smoother edges mean electrons flow more freely, leading to better electronic components.
Okay, so they figured out how to make these amazing near-perfect nanoribbons in large quantities. The next obvious step is, did they work? How do they perform in actual devices?
That's exactly what they tested next. They immediately started building devices, focusing first on those field effect transistors, the FETs we talked about.
So tiny switches.
Right. They built a typical FET using a BPNR that was about 13 nanometers wide. And they did something else important. They used graphene contacts.
Graphene. Not regular metal for the connections. Why graphene?
Another clever move. Sometimes where the metal contact meets the semiconductor, you get resistance, like a little electronic speed bump. It wastes energy and slows things down.
Ah, contact resistance.
Exactly. But the researchers found that using graphene, which is another amazing 2D material, dramatically reduced that contact resistance. It created a much smoother connection for electrons flowing in and out of the nanoribbon.
So like having a perfectly smooth on-ramp and off-ramp for the electron highway.
That's a great analogy, and the results were stunning. This FET achieved an on-off current ratio of 1.7 million, meaning it switched off incredibly cleanly. And its field effect mobility, which is basically how quickly electrons move through it, was 1,506 centimeters squared per volt second.
Okay, those numbers sound impressive, but put them in context. How good is that, really?
It's exceptionally good. That performance is better than any previously reported FETs made from black phosphorus nanoribbons, and even better than those made from the 2D black phosphorus sheets people struggled with before.
Wow. So this unzipping method plus the graphene contacts really delivered.
It really did. And as Chengxin Chen from Shanghai Jiaotong University pointed out, this is significant because BPNRs avoid problems seen in other nanomaterials. Like carbon nanotubes can be metallic or semiconducting, which is tricky for consistency. Graphene nanoribbons don't have quite the same ideal combination of mobility and band gap. These BPNRs are purely semiconducting and tunable, offering a potentially cleaner path forward.
Okay, so supercharged transistors are a huge win. Did they test these nanoribbons for anything else?
They did. They also made photodetectors with them.
Light sensors.
Yep. They used a slightly wider ribbon, about 18 nanometers, and found it made an excellent photodetector. It was incredibly sensitive to light. High detectivity, high photoresponsivity were the technical terms.
Meaning it could see very dim light and turn it into a strong electrical signal very efficiently.
Exactly. And it was fast, too. Its response time was less than 100 microseconds. So think camera sensors that are way more sensitive and react much faster than what we have now.
That's really impressive. So connecting this back to the big picture,
Right.
what's the overall impact here?
Well, people in the field are definitely taking notice. Kawi from the National University of Singapore, for instance, called these results a notable breakthrough, especially for the mass production aspect. This work really does lay a foundation for next-gen electronics and optoelectronics that could be significantly better performing and more energy efficient.
It really sounds like black phosphorus nanoribbons are poised for prime time. But I imagine there are still some hurdles before we see these in our phones, right? What challenges remain for wide adoption?
That's a fair question. Yes, there are definitely challenges still. Two big ones, really.
Okay, what was the first one?
Uniformity. While the unzipping method makes lots of high-quality ribbons, they aren't all exactly the same width. And remember, the width determines the band gap.
Ah, right. So if you want millions of identical transistors on a chip, you need millions of identical nanoribbons.
Precisely. So they need better methods to sort the ribbons after making them, to select only the ones with the specific width needed for a particular application. That kind of post-processing and separation is crucial for consistent device performance.
Makes sense. Consistency is key for manufacturing. What's the second big challenge?
Assembly. Directional assembly, to be specific. Right now, they can make lots of these tiny ribbons, but they're sort of floating around in a solution. To build complex circuits, you need to take these individual nanoribbons and place them precisely where you want them, all aligned in the right direction.
Like laying out millions of microscopic wires in a perfect pattern on a chip.
Exactly. And doing that reliably and quickly on a massive scale is, well, it's a huge engineering challenge at the nanoscale.
Okay, so making them is one thing, but sorting them by size and then arranging them perfectly is the next mountain to climb. Do the researchers, like Chengxin Chen, talk about these next steps?
They do. They explicitly state that their next focus is on developing strategies to get high-quality BPNRs that are both uniformly wide and unidirectionally aligned. Solving that alignment and uniformity puzzle is absolutely vital for building actual integrated circuits with these things.
It sounds like they know exactly what needs to happen next.
Yeah.
Okay, let's wrap this up. If you had to boil it down, what are the main takeaways from this deep dive?
Okay, first takeaway. Researchers, specifically the team at Shanghai Jiaotong University, figured out a really clever way using that pre-stress and sonic unzipping to make huge amounts of incredibly narrow, high-quality black phosphorus nanoribbons. The 95% yield is a game changer.
Right, the manufacturing breakthrough. What's number two?
Number two, these nanoribbons, especially when combined with smart choices like graphene contacts, enable transistors and photodetectors that blow past previous performance records. We're talking serious improvements in efficiency and capability.
Better performance unlocked. And the third point.
And third, this isn't just cool science in a lab. It's a really crucial step towards building the actual next generation of computer chips and sensors. It pushes the limits of what's possible, paving the way for devices that are smaller, faster, and use way less power.
This really highlights how deep material science working at these tiny scales can lead to genuinely astounding leaps in technology. It feels like we're getting closer to a whole new era of electronics.
It definitely feels that way.
So it leaves me wondering, considering the incredible speed and sensitivity these tiny nanoribbons offer, What kinds of really revolutionary technologies, maybe in medicine, maybe in AI, things we can barely conceive of today, might actually become possible thanks to breakthroughs like this?